In section 9.2, we look into something called a partial derivative. So you are already familiar with a derivative from your Calculus 1. And if you have a graph of a function, and if you were trying to figure out the derivative at x equal to a, then you were trying to figure out the slope of the tangent line at this point right here. To get things started, you said, let's go a little bit to the right, h units to the right, and consider this other point. And you were going to consider the slope of this secant line, and the idea was that the slope of this red secant line was a good approximation to the slope of your tangent line. And the way that you computed the derivative, your derivative at a, was through this computation of the limit as h goes to 0 of f of a plus h minus f of a divided by h. The change of the y values divided by the change of the x values. So that's how you got the conversation started when you were talking about derivatives. But later on, when you had functions such as f of x equal to, let's say, x to the fifth, you really didn't refer to that computation to compute a derivative. You simply used the power rule for this kind of example, and you got 5x to the fourth, and you were done with that problem. To analyze partial derivatives, it's taking the derivative of a function of many variables. Suppose that we're looking at things on the three-dimensional coordinate system with your x coming out of the page, the positive y's towards the right, and the positive z's going to the top. You could consider a function f of xy as being this surface. And suppose you were doing your analysis at a comma b. So suppose that you went out a units this way, b units that way, and you were going to consider this point right here, which would be your f of a comma b. Consider drawing a curve that makes one of these variables constant and the other one free to change. So consider in your function f, made up of x's and y's, to keep one of the variables constant. So how's about we make that b constant? If you try to interpret this on that graph, it would be this curve right here, representing the collection of points on that curve where the b is a constant value. And then we would care to figure out the slope of this curve in that direction. Let me use green. The slope of this green curve is going to be the partial derivative of f with respect to x. So again, the slope of this red curve is what we're calling the partial derivative of f of x. Let's say f of xy with respect to x at the point a, b. This could be written in a shorthand kind of way, in this really stylized kind of derivative notation. So it's the partial derivative of f at with respect to x at the point a comma b. Another notation for this would be f with a subscript of x. So this is pretty much telling you that you're taking the partial derivative of f with respect to x, and you're evaluating it at a comma b. To get a better grasp of what's going on, I'm going to take you to GeoGebra 3D. And in GeoGebra 3D, let's suppose that we're working with this surface 1 over 3 x squared plus y squared. This guy would be a paraboloid, kind of like a parabola, but in 3 dimensions. And here you have, again, the x-axis coming out towards you, the y, positive y is to the right, the positive z is up. And suppose that we're trying to compute the partial derivative of f at the point 1, 2. So on the right-hand side, the point 1, 2 is this point that's blinking. So you plug in 1 for your x's, 2 for your y's, and then you would get the z value to be the height of this curve. So again, you would plug in 1 for your x's, 2 for your y's, so 1 squared, that's 1. 2 squared, that's 4. So this guy is 5. So multiply times 1/3, so that height is 5/3. So consider if I were to keep the y value constant and allow the x value to change, then you would be looking at this collection of points on that graph. So again, the black points are the collection of points where the y value is constant and the x value is allowed to change. Consider what I can do if I turn off the graph and rotate the positive x-axis to the right-hand side here and make a comparison between just the x's, trying to get it just right, just the x's and the z values, the values of the function f of xy. Then you have a curve just like you had the curves back in Calculus 1. And that partial derivative is trying to capture the slope of the tangent line. Okay, so let me go back and reset this. We could also talk about the partial derivative of f with respect to y. So again, let me copy this picture. Most of the things are going to be exactly the same. So again, let's suppose that I'm trying to do my analysis at a comma b, and this is the z value, a comma b comma f of a comma b. And now let's suppose that we're looking at a curve on this surface where the a's are constant. So it would be that red curve. And we can consider the slope of this curve in that direction. So again, the slope of this curve is practically the same thing we had over here, but with respect to y. So this is known as the partial derivative of f of xy with respect to y at the point a comma b. And just the same, you can denote this as partial derivative of f with respect to y at ab, or as f with a subscript of y here evaluated at ab. Back to GeoGebra 3D. If I'm considering the curve that holds the x to be constant and allows the y values to range, I have this collection of points. So again, for all of these points, the x coordinate is all 1. And the y values are allowed to change. If I turn the graph off and compare the y-axis and the z-axis together, I get this curve. And the partial derivative of f with respect to y is asking you, what is the slope of this tangent line at that point A? Just as we talked about derivatives using this limit, you can compute the partial derivatives using a similar computation. So if you're computing the partial derivative of f with respect to x at the point a comma b, you can write this as a limit as h goes to 0 of the following difference quotient. If we're taking the partial derivative of f with respect to x, that means that the y value is considered to be constant. So on the top I have f of an ordered pair, and the y value is going to be b. And over here, f of an ordered pair, the y value is going to be b. Because again, if I'm taking partial derivatives with respect to x, the y value, the y variable, is considered to be constant. For the x coordinate, this guy will be a plus h for the first one, and a for the second one. So this numerator gives me the difference of the z values for my function f of x, y. And on the bottom, I'll have the difference between this value of x and that value of x. What's the difference between those two values of x? Simply h. So the computation looks very, very, very similar to the computation for the derivative of a function of one variable. And in the same way, the partial derivative of f with respect to y at ab, because we're taking the partial derivative of f with respect to y, what kind of value does the x have? It has to be a constant. So on the top, where you have the difference between two evaluations of your function f, the first coordinate is going to be a for the first and a for the second, because the a values are considered to be, or the x values are considered to be constant. For the y values, those are the ones that are changing. So this guy is going to be b plus h, and b for this guy. That gives you the difference of the z values on the numerator, and on the bottom, the difference of the y values, and the difference of those two guys is simply h. So this is how we're defining the partial derivatives of a function of two variables. But in the same way that you really wouldn't use this difference quotient to differentiate x to the fifth to get 5x to the fourth, when taking partial derivatives, you really wouldn't use these formulas unless absolutely necessary to compute partial derivatives. Consider this extra problem. Let f of x, y. Let's work with the graph that I had up on GeoGebra 3D. My 1/3 x squared plus 1/3 y squared. Consider the partial derivative of f with respect to x. So I'm taking the derivative of this expression with respect to x, and wherever I see a y, I'm going to assume it's a constant. So what's the derivative of this guy with respect to x? Well, that will be 2/3 x to the first power. What's the derivative of that guy with respect to x? Again, I'm assuming that y is a constant, so the derivative of a constant is 0. So you don't have to really write anything, but I'm just going to put plus 0 here just to remind you that it's 0. And what would be the partial derivative of f with respect to x? at for this expression. Not with respect to x, excuse me, with respect to y, we already did x. The partial derivative of this guy with respect to y is going to be 0, and the partial derivative of that guy with respect to y is going to be 2/3 y to the first power. Done. Huh. Okay, let's do one with a little bit more detail. Let's say we have x squared minus 3 x squared y to the 4th. What can you tell me about the partial derivative of f with respect to x? Well, the derivative of this guy with respect to x is simply going to be 2x. And within this expression, this guy is a constant and that guy is a constant. So right off the bat, I can just copy and paste those guys exactly as they were before and focus solely on taking the derivative of x squared. What's the derivative of x squared? Well, that's 2x. So this partial derivative is 2x minus 6 y to the 4th times x. Done. What about the partial derivative of f with respect to y? The partial derivative of x squared with respect to y is 0, so that goes away. And to take the partial derivative of negative 3x squared y to the 4th, I'm going to consider this negative 3 a constant, and also this x squared a constant, because again, x's are constant when I'm taking partial derivatives with respect to y. So I'm just going to copy and paste the negative 3x squared and focus solely on taking the partial derivative of y to the 4th with respect to y, which is 4y cubed. So simplifying this, that's negative 12x squared y cubed. So partial derivatives can really be a piece of cake.